Hey, welcome back. So let's look at unit cells in 3 dimensions. So we might be interested in 2 dimensions, but most materials are 3 dimensional. So it turns out there's 7 different unit cell shapes in 3 dimensions, and I'm not going to try and draw them. Let me just pull up a picture here. All right, so here they are. So if you want to repeat anything in 3 dimensions, right, if you've got blocks that you want to stack one on top of another and you can't have any space left in between, there's actually 7 different blocks you can do it with. The cubic one's really the one that we'll probably spend almost all our time looking at here, just because I think it's the easiest one to draw. But if you're a geologist or a solid state chemist, right, you probably want to know about the other ones. So the other ways you can arrange it are tetragonal. So whereas these are like cubes, these are sort of like the regular bricks that you might build a house with. Here are ones where all 3 dimensions are different, but you can see all of these have got right angles here, and you get these weird shapes here, these hexagonal, monoclinic, triclinic, and rhombohedral, where these angles are not 90 degrees. So they're weird shaped bricks, but they will fit together, and you can make copies and reconstruct any crystal structure using one of these 7 different shapes here. So let's focus on the cubic unit cell. So it turns out there's actually 3 different kinds of cubic unit cells. And I'm going to go ahead and try and draw these unit cells out. So I'm going to put dotted lines here for the ones that are kind of behind the front faces of the cubic cell here. So that's my poor attempt at a cube. And although the molecules and atoms themselves are kind of large and there's not a lot of wasted space here, I'm going to shrink them down to little dots. So the simplest one is the simple cubic. So that makes sense, right? And in the simple cubic one, there's actually a particle at each one of the 8 corners. And so these red dots here, if you like, are my lattice points. And the lattice points are where we're going to go ahead and place things like atoms and molecules. But if you're crystallizing out things like viruses, right, there could be a virus at one of these lattice points. But most of the time we'll be looking at atoms and ions and molecules attached to these lattice points here. This one here is not a very good way to pack matter. It turns out that it's only 52% efficient at packing matter, so it's got a 52% packing efficiency. So if you go ahead and you try and pack spheres, then it turns out that you just barely use half of your space if you use this kind of arrangement. And if you're actually looking at atoms here at the lattice point, so if each lattice point is actually an atom, you can see that there's only 1/8 of an atom inside of this cubic unit cell. So the reason for that is that you can, of course, get 8 cubes to pack together at that corner. So sort of 4 on a top layer and 4 on a bottom layer, that's 8. And so that blue atom there would be shared between 8 atoms. So only 1/8 of that would be inside that cubic unit cell. Because this packing efficiency is pretty lousy, there aren't too many materials that actually pack this way. So the one that the textbook mentioned is polonium, or PO. So polonium, which is a metal, actually packs its atoms using this simple cubic way. So I didn't title this, did I? So I should go ahead and write, this is simple cubic. So this is one of the 3 different ways that matter can be packed using a cubic unit cell. If we're using atoms and we're placing atoms at the lattice points, we can actually go ahead and calculate how many atoms are inside of this unit cell. So there's actually 8 atoms at the corners, and each corner only is 1/8 inside of the unit cell. And so actually that gives us a single atom per simple cubic unit cell. So this is a very lazy way to pack because that cell itself essentially only contains 1 atom. So this is an app I have on my iPad, and this actually is something you can download from the App Store, and it shows you a bunch of different unit cells. And this is polonium. Polonium has that simple cubic unit cell. We can spin it around and just kind of look at the atoms at the edges there. So they've been shrunk down in size just to make it easier to see. But if we look at them full size, right, clearly they're touching. You can't have all those empty spaces, otherwise it wouldn't be a solid. And that is just a single unit cell there. So notice each atom is only 1/8 of the way inside. We can go ahead and we can replicate that. We can go ahead and make 8 copies of that and stack 8 one on top of the other. And you can see that atom in the center is actually surrounded by 8 different unit cells. So each atom is only 1/8 of the way inside of that unit cell there. And again, if you turn on the full size version here, you can see, right, the atoms are touching each other. There's really not a lot of space there in between. And this is a 1 nanometer cube, so I've gone ahead and replicated this 5 or 6 times in each dimension. And you can just kind of see how all those atoms kind of line up in lines. It's very interesting to see. In fact, we know these structures by scattering X-rays off of these lattice points, right? So these crystals actually scatter light, just like the grooves on a CD or a DVD or a Blu-ray give you little rainbows.